Thank you. Thank you very much, and thank you to Vanishing Ink for making this available to everyone. Let's give them another round of applause. I think that's wonderful. I appreciate it. All right. Well, I think just to get me in my comfort zone, and I know some of you are at the lecture and most of you are at the gala, I'm going to get started doing a quick version of my show, and then we'll go on into explanations, okay? And so, so to begin, I'll need a few people on stage to help me out who have a calculator. If you have a calculator with you and you're comfortable using it, raise your hand. Let me get a few people to help me out. I see 1 and 2 and 3. Would the 3 of you bring out your calculator? Join me up on stage. Give them a round of applause. Coming up. Fantastic. Right this way here. Now, since I have not had the chance to work with these calculators, I need to make sure that they are all working properly. Would somebody get us started by giving us a 2-digit number, please? Any 2-digit number? 42. And another 2-digit number, sir.
36.
Multiply 42 times 36. Make sure you get 1,512 exactly, or the calculators are not working. Are they all working? Give them a round of applause. And I notice that took some of us a little time to get the answer, and that's okay. I'll give you a shortcut for multiplying even faster. There's something called the square of a number, which all of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25, 6 squared would be 36, and so on. Now, most of these calculators have little shortcuts for squaring. If you know the shortcut, like on the iPhone, you can do 5 and times and equals, and that gives you the square just like that. That's a shortcut the calculator uses to do it faster. What I'm going to try and do is to square in my head 3 2-digit numbers faster than they can do on their calculators, even using the shortcut method. What I'll ask is 3 people here in the first row, 1, 2, 3, each yell out a 2-digit number, and if you would square the first, the second, and the third one, I will try and race you to the answer. So quickly, a 2-digit number, please. 39, okay, next. 83, and one more. What was that? 78. Would you call out your answers, please?
1,521.
1521. 6889. Give them a round of applause. Let me try to take this one step further. I'm going to try to square some 3-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone at all call out a 3-digit number. Anyone on our panel verify the answer. And if I get the answer right, either give me a thumbs up or show your calculator. If I make a mistake, let me know and I'll try and fix it. A 3-digit number. 628 is 394,384. 394,384. Good. How about another 3? Oh, I heard so much. All right, raise a hand if you want to give me a. So a 3-digit number. What was that? 320 is 102,400 exactly. Good. How about another 3-digit? 989 is 978,121. Thank you very much. Let me try to take this one step further. I'm going to try to square a 4-digit number this time. I'm not going to beat you to the answer on this one, but I will try to get the answer right. To make this a little bit more random, how about we take second row this time on this side? Say the first 4 of you call out a single digit between 0 and 9. That will be the 4-digit number that we'll use. 8, 5, 3, 7. This will take me a little bit of time, so bear with me. 72 million. 880,369. Good. Thank you very much. And let's give our volunteers a nice round of applause. Thank you. Thank you very much. Yeah. All right. For my next number, still like that line, I'd like to present something that we mathematicians refer to as magic squares. Now, I have done such an extensive study on magic squares that I'd love to create one for you right before your very eyes. But for this, I'll need another assistant here, someone here I do not know. And how about the young man over there? Are you willing to help us out? Sure. Come on up here. Let's give him a nice round of applause. All right. Oh, I'm so jealous. Okay, right over there. Stand right over there. And what's your name, sir?
I'm Blake.
Blake, and Blake, if you would stand right there, I'm going to ask one more question, and if it's too personal, I can change the question. Blake, are you willing to share with us your birthday, including the year?
Okay.
Great. Blake, what is your birthday?
April 2nd, 2010.
April 2nd, 4/2/2010. So now, Blake, if we were to add the numbers in your birthday together, let's see what we get. We've got 4 plus 2 is 6, plus 20 is 26, plus 10 is 36. So 36 becomes your magic number. What I'm going to try and do now, Blake, is to fill out this box in such a way as to get your magic number appearing here as much as I possibly can. This will take me a couple of seconds, so bear with me here. I think that works. Blake, would you choose for us any row? Row number 2, 3, or 4? Which would you like? 4. All right, class, together. 2 plus 2 is 4, plus 12 is 16, plus 20 is 36. The odds were 4, 6, 26, 36, 19, 30, 33, 36, 11, 32, 33, 36. Would you choose a column, Blake? 1, 2, 3, or 4? 2. All right, class, 2 plus 11 is 13, plus 21 is 34, plus 2 is 36. The odds were 4, 23, 34, 36, 20, 23, 24, 36, 10, 13, 16, 36. How about that? Now, Blake, I am not through with you. I decided, since this was your magic square, based on your birthday, at no extra charge, I would give you these diagonals as well. Check it out here. 2 plus 21 is 23, plus 3 is 26, plus 10 is 36, 4, 15, 16, 36. But I didn't stop there either. I decided, since this was for Blake, wouldn't it be great if we could get these 4 in the center to add up as well? Check it out here. 21 plus 11 is 32, plus 3 is 35, plus 1 is 36. But did I stop there? No. Blake, you may have noticed I put a little extra attention in that corner. I did that so I could get these 4 squares. 4 plus 2 is 6, plus 11 is 17, plus 19 is 36 to add up. And I figured, heck, as long as we got that group of 4, let's have a party. We may as well get this group of 4, 20, 30, 33, 36, 11, 32, 34, 36, 1, 4, 24, 36. But did I stop there? No, I said Blake wouldn't be happy unless we got this group of 4, 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 this group of 4. Now, I have to apologize, Blake. I was not able to get this group of 4 nor that group of 4 to add up, but I had to do it that way. If I was going to get these 4 in the corners, I knew that would be important to you. 4, 14, 34, 36. But wait, here's the cool part. Not only do those 4 numbers in the corners add to 36, if you look at them closely, you'll see we have 4, 2, 2010. So please keep this as a souvenir from me, and let's all give Blake a nice round of applause. Thank you, Blake, very much. Thank you. One more round of applause for Blake. Phew. Got one more question for the audience before we get into explanations. By any chance, does anyone here happen to know the day of the week that they were actually born on? If you think you know your birthday, raise your hand. All right, just gentlemen here. What year? Just the year? 1958. 58, and what month? January what? 21st. Was that a Tuesday? Fantastic. How about you, sir? What year? 80. And the month? November what? 12th. Was that a Wednesday? Fantastic. How about yours? What year? 2004. 2004, you said? And the month? May. May what? 18th. Was that a Tuesday? Excellent. And how about one more towards the back in the hat? What year? 54. And the month? February what? 13th. Was that a Saturday? Thank you very much. Are there any questions? No? Okay. So folks, what I'd like to do in this first half is to explain to you everything you've seen me do up here. And depending on how the timing works, maybe a few other things that will make you look like a genius without really trying, right? And then we'll go into some other bits of mathematical magic in the second half. First, let me quickly, and I know I did some of this in my lecture, and it seems like about 2/3 of you were there at the lecture. But, you know, as a math professor, I know it never hurts to have a little extra review, right? The first time we hear it, it sort of makes sense, and the second time we really have it. So let me first show you the method that I use for squaring numbers, at least 2-digit and 3-digit numbers, and then later at the end of today, we'll do 4-digit and higher just to see what's going on for that. Let's try give us a small 2-digit number as our first example. 21, great example. So 21 is not a difficult number to multiply, but what number close to 21 is even easier? 20, yeah. So I'm going to go down 1 to 20. I like 20 because it ends in 0. And I'm going to go up 1 to 22. So the first part of my calculation is I do 20 times 22, which is 2 times 22, with our friendly 0 attached. 2 times 22 is 44, so 20 times 22 is 440. And that's almost the answer. To get it exactly, we only have to add the square of the number we went up and down. We went up and down 1. 1 squared is 1, and there's your answer, 441. Okay? Let's do one more example, and then I'll take it up a notch higher. How about another 2-digit number, sir? 74. Okay, so this is a harder one. In fact, it's about as hard as they come. Okay, so if you don't see it this first time, it's totally understandable. This does take a little bit of practice. But what do? We go down 4 to 70, up 4 to what? 78. Okay. Now we do 70 times 78. Now, again, that's 7 times 78 with a 0 attached. I'm going to do this slowly. 7 times 70 is 49 with a 0, 490. 7 times 8 is 56. 490 plus 56 from left to right is 546. We're almost there. Attach the 0, and all we have to add to this is what? The square of 4, which is 16, and there's your answer, 5,476. Thank you very much. Now, because the math professor in me insists that I not only show you how, but briefly why, right? Because, you know, what is this crazy method we're doing here? So what I'm asking you to do is to square a number. Let's say we're looking at a squared. And I'm saying that what you should do is take a and go down some distance d, then multiply it by a when we go up the same distance d, right? We're doing a minus d times a plus d, and then we're adding what at the end? D squared. And is that going to work? Well, if we take a minus d times a plus d, any of you that still have those fragments of algebra can say that that multiplies to what? Oh, a squared minus d squared, yes. And then when we add the d squared, the d's cancel, and we're left with a squared. Let's hear it for algebra, right? Honestly, if I were teaching algebra and the students would say, why do we have to learn all this? Well, this is at least an application of that they might find cool, right? I don't do the algebra. I don't think explicitly about the algebra when I'm doing these calculations, but it gives me the confidence to know that this method is going to work whether I'm squaring 2-digit numbers or 3-digit numbers or anything. So here, let's go up one more level, and I'll show you what I do for squaring a 3-digit number. A question, yeah? Yes? Yes. I always calculate from left to right, not right to left. That is, you know, because we read numbers left to right, we pronounce numbers left to right. We say 5,476, not 6 and 70 and 400 and 5,000. And with a little practice, you can, what did I say? With a little practice, you can and should calculate left to right. And so, when I was a kid and I started developing my own methods for doing mental math, the reason I worked from left to right was almost a magician's motivation. I wanted to be able to start to say my answer while I was still calculating the rest of the answer, right? Because people mentally, they stop timing you once you start saying the answer, but I'm still calculating it as I'm saying it. You know, and I do the 70 times 78. I know enough to know this is going to be 5,000 after I've done this, and I've got 5,460 plus 16 is 5,476. So as I'm doing that adding of 16 while I'm saying the 5,400. And that was my initial motivation. But I think cognitively, there are lots of reasons. And just for practical applications, it's more, if working left to right, while your brain is clear, you're getting the most important, the most significant numbers. It's more important to know that your answer is a little over 5,000 than to know that it ends in 6. Right? And so by working left to right, even if you just want to get a good approximation for your answer, you know it right away instead of saving it for the end. Another question.
When you start saying you start with 78, you go up to 80?
Oh, yeah. So here, I always rounded up or down to the nearest multiple of 10. If this had been 78 squared, I would go up 2 to 80, down 2 to 76. 8 times 76, 560 plus 48, is 608. So that becomes 6,080, which I can start to say as I add the number 4. So it's 6,084. Okay? And again, the algebra bears that out. You take the number A, you go up a distance d, you then balance it by going down the distance d, and multiply them together. One last question, because I want to make sure I get to other stuff here. Yeah. That's right. D can be anything. If you wanted to do 74 squared by doing 75 times 73 and adding 1 squared, you could do that, but that would be as hard as the original problem, right? But it works, it does. And so when I square a 3-digit number, for example, I am always rounding up or down to the nearest 100. Give us a 3-digit number this time. 336. Now, let me give you the answer first. So 112,896. Now, when I did this calculation as warm-up to square the number 36, you go up 4 to 40, down 4 to 32. 40 times 32 is 1280, plus the square of 4 is 16 to get 1296. I do have to confess, I've been squaring numbers for such a large fraction of my life that I know the 2-digit squares, especially the ones up through 50, by heart. But here they are, 1,200. But the 3-digit numbers, I don't have any of them, almost any of them memorized. I really have to calculate it. So, but that's helpful because when I do 336, I'm going to round it down to 300. I go down 36 to 300, up 36 to 372. This is the hard part, right? I have to do 3 times 372 with my 2 friendly zeros attached. 3 times 300 is 900. 3 times 72 is 216. When I add them, I get 1,116. That's 111,600. And what do we add to that? 36 squared, which fortunately is staring us in the face. We add 1,296 to that, left to right. Notice there's only a little bit of overlap, and we get 112,896. Let's hear it for algebra.
Yeah. You said it's staring you in the face, but if you're doing this mentally, and you do the 36 squared first, how do you remember 1296 after you've done all this calculation?
That's a great question. How do you remember? You have to be very, very quick at the 36 squared, and in my case, I know it instantly, because otherwise what will happen is you get the 111,600 maybe. You said, now I have to add what? If you're lucky, you remember you have to add 36 squared. You do 40 times 32, 1280 plus 16 is 1296, and you add it to, it's gone, right? So what? Only if this is so fast that this number is still ringing in your ears. And I say ears, not eyes, because for me, this is an auditory process, not a visual one. That's surprising because I'm showing it to you visually, but in my head, it's auditory. In the same way that if I asked you, what's 5 million plus 3 million, you all say 8 million, not because you visualized a 5 with 6 zeros and a 3 with 6 zeros, but because you know 5 plus 3 is 8, that's hardwired, and the word million comes for the ride, right? Same thing is happening here. Words like hundreds, thousands, millions are lining things up, not in my eye, but in my ear. Now, I do run into that memory problem once I start squaring 4-digit numbers, because I...
But before you
Yes.
go there, when you were learning this or teaching it to yourself or developing it,
Yes.
and you didn't have all the numbers,
The 2-digit... Well,
2 digits squared in your head,
but I would say don't... You know, when I started doing these sorts of problems, the 3-digit squares took me as long as, say, the 4-digit squares take me now. So it's okay to pause and think and
use the alphanumeric conversion.
not. I think you'll be surprised how many of the 2-digit squares you maybe already know or can calculate pretty quickly, like maybe about half of them. That before those, and you only need to know the ones up through 50, because when you're squaring a 3-digit number, you're always rounding up or down to the nearest 100. So I'm never going to have to travel more than 50 to get to my number. So it's not like you have to know 83 squared. You know, you already know 1 through 10 squared. Maybe many of you through frequent use know 10 through 20 squared. You know 30 squared, 40 squared, 50 squared, 25, 35, 45 are easy to do. We're already over half of those 2-digit numbers that you need to know, right? The last problem that was given to me when I was squaring 3-digit numbers on the stage, one of you said 989. Let's do that one and see how we would do that with this method, right? We would go up to what number? 1,000. 1,000. We go round to the nearest multiple of 100. There, we went up 11 to 1,000, down 11 to what? 978. And so 978 times 1,000 is 978,000. And I'll just say 978,000 while I add the square of 11, which you might know is 121, and there's your answer, 978,121. Right? Well, thank you. You know, so that's what's going on there. When the problems get bigger, I do have to resort to using a phonetic code and memory tricks. I'll show you that in the second half. Okay, but I just wanted you to have a sense of what's really going on in my mind. Okay, all good? We're good on that? All right. Let's move on to the magic square, because I know from experience that this is the part of the lecture that magicians have found to be most interesting, and everyone is surprised how easy it is to do with just a little bit of practice. I mean, you can get this, you know, over lunchtime. You could say, oh, I'll make a magic square of my own birthday, my family's birthday. So here we go. And I'll need somebody to volunteer their birthday for me. Okay, Dan, what's your birthday?
May 9th, 1964.
May 9th, 64. Now that's a very nice number because I have all 1-digit numbers there, right? We'll do a second example when it's not all 1-digit numbers, but 5964. For anyone born in the 1900s, that's how I write it. I don't write 19 and 64 because the 64 is such a big number, it's just ugly and ruins the aesthetic of the magic square, right? So in the 1900s, I just write the last 2 digits of the year. For people born in the 2000s, that I'll do that as my next example, I'll write 20 here and then a 2-digit number over there, like 2010 we did for Blake, right? We had a 20 and a 10. Okay, so step 1. Add these 4 numbers correctly. If you mess up here, there's not much you can do, right? So 5 plus 9 is 14, plus 6 is 20, plus 4 is 24. I write that nice and big for my audience to see, but also for me, because I'm going to be using this number a lot. Okay, now, here we go. I always fill out the magic square in the same order, and all you have to remember is we're going to start by going up this diagonal, okay? And once you're here, after you get these 3, you'll be on autopilot, all right? Here we go. Now, because you've seen Blake's magic square already, you know that the birthday not only will appear in the top row, but also in the 4 corners, right? So what number must go here? 9. And that's the first number I write down. And what number must go there? 6, right? This 6 up here, right, has to go there. But that's the last number I write down because I don't want to give it away too soon, right? I don't want people to see that. But by the way, I'm going to say there are a lot of advantages to using this double birthday magic square. And let me just tout them now so I don't forget to say it later. First of all, more than any of the other magic square methods out there, this one is personal. This is one that the person who's on stage in the audience, if you just said, give me a number between 30 and 100, they don't have any more attachment to that number than they do the random card that they chose from the deck, right? But when it's their birthday, then wow, that's personal. They keep that as a souvenir. And moreover, you might have memorized the magic squares for everything from 30 to 100, but you're not going to have memorized all the possible birthdays. So it seems more impossible. It feels more personal. They care about it. You can get enthusiastic because you're creating it for them. This is Dan's magic square. And unlike any other magic square method that I know of, it has a surprise ending. It has a natural ending. It's not like we just keep doing it until we're exhausted and take your bow. We get that the birthday appears in the 4 corners, and that's like a nice little button to put at the end of the trick, right? So that's why I like this method so much. This is my own method. Feel free to use it. It was inspired by an article I read in Genie, written by Harry Lorraine in the early 2000s, 2004 or something like that, where he said, oh, you can actually take start with any 4 numbers or any row and make a magic square out of it. So this was, ultimately, this is what I came up with, which I think is really simple. Okay, so here we go. You start with a 9. Okay. The only thing you have to remember just about is what goes here, okay? Now, truthfully, you can put any number that you want here, and it'll still work. You can put any number you want here, it'll still work. The only number you don't want to put here is the number that's sitting in the 3rd position. You don't want to put a 6 here, because if you do, everything will add up to 24, but it'll be the same 4 numbers in every row and column. It'll be a 5, 9, 6, 4 in some order, and that won't look very magical, right? On the other hand, the farther you get away from this number, the more likely it is that negative numbers could creep into the magic square, and I try to avoid negative numbers if possible, and 95% of the time you won't need them. Right? You want to avoid them, but it still works. I mean, in the worst case scenario, I have a -1 sitting down here, and that's it. Everything else is positive, okay? So anyway, so the way I avoid that is I just take this number and I add 1 to it. So if this is a 6, then this number here is 7. Again, we take this number, add 1 to it, and there's your 7. If you want a pro tip, if the month is January, then instead of adding 1, I subtract 1, and that helps me avoid a negative number. But that's, if you want to, if it's January and you add 1 to it, you're going to have a -1 sitting over here, and that's fine, right? But that's it. Okay, so now it becomes almost like the easiest Sudoku you've ever tried, right? Because we know that this diagonal has to add to 24. And I have 3 of the 4 numbers already, 9, 7, and 4, which add up to 20. So what does this number have to be to give us 24? 4. Okay. Now we go on and we say, hey, we remember with Blake's magic square that this group of 4 would also add up, right? And I have 3 of the 4 numbers. So we add the 3 numbers, 4 plus 6, that's 14. And all you have to get 24, you're going to have 10. Now, by the way, yes, it's always this number plus 1, but I don't want you to have to memorize anything. You're going to forget the formulas. Just do the math and get the number and that's what I'm doing. I don't have almost anything memorized. So then I go 4 plus 6 plus 9 is 19, which makes this a 5. All right, then I go to this group. 5 plus 9 is 19, which makes this another 5. Okay, now do you remember, this is important, remember with Blake's magic square, I said I was not able to get this group of 4 nor that group of 4 to add up, right? Don't try to make this add up. If you do, you will mess up other important things down the road. That's the bad news. The good news, actually there's 2 bits of good news. One is it's okay if you point out that some things don't add up. It just makes it look like it was all the more impossible. And you say, but I had to do that if I was going to get these 4 corners to do it, and everyone says, oh, that's really great. So that's the bad news. The good news is the way the algebra works, these 2 numbers are always the same, and these 2 numbers are always the same. So you don't have to do any arithmetic. You don't even try to get this thing to add up, because don't do it. We just slide this 5 over, and that works. In fact, you could check it out. This column, 5, 5, 5, 9, adds up to 24. But I don't even have to do the math. I just slide this 5 down. I could slide that 4 down, and that's going to work. Okay, now, what's your question?
How did you get the first, the 5 next to the 4?
In order, I do 9. 6 plus 1 is 7. Here's your 4. Now you're asking about this 5. I went to this group of 4. So at this point, I had 4, 6, and 9, which is 19, which made this. And then I'll just go on one more step. And then I did this group of 4. Thanks for asking. 5, 5, and 9 is 19, which gave me this 5. All right? And then I had this 5. Now, there's not normally this much repetition. It's only because Dan happened to have a 4, 5, and 6 in his. All the numbers in this chart, except for 2 of them down below, are 1 away from numbers up here. And 2 numbers over here are 2 below the numbers up here, right? And that's it. They're all very close together. So if your numbers were pretty close together up here, they'll be pretty close together in your square. I'll show you the algebra in a minute. Okay, so now we go to the middle. 7, 4, 5 adds up to 16, which makes this 8. 7, 5, 9, I go to this group of 4. 7, 5, 9 is 21, which makes this 3. Then I do this group of 4. 3, 7, 8 is 18, which makes this 6. Your brain's getting tired from all the adding and subtracting, so I save the easiest parts for last. This number is going to be what? 4, just slide it down. And this number is going to be what? 6, and that's the secret of the magic square. Thank you very much. I see some questions. You had your hand up. What's your question?
Yeah, I have 2 questions.
Yes.
So you had the first row set 5, 9, 6, 4, and then you immediately got the 9 at the bottom left. But how did you get to that 9? And why not 6?
Well, because I want the punchline of this is that, but here's the cool part, not only do the 4 numbers in the corners add up to 24, if you look at them closely, we have 5, 9, 64, right? And so that's their birthday again, which makes it especially nice to end it. And that's why I'm going, this is the 9 and this is the 6, so that it's in that order.
And my second question was, when you're going from the bottom to the top right in that diagonal, you said you could just add 1 to the 6, right? But you could just easily add 2.
If I add 2, every number that I add, extra number I add here, takes away a number from here. So yes, I could add 2, and that would have been fine. If I'd added 3, this thing would have become a 0, or a 1, actually. If I'd added 4, it would have been a 0. If I added 5, it would have been negative. So the farther you get away from this number, the more likely it is that negative numbers will show up in the square. And I have found that it's just as nice to have, I don't complicate things. I just add 1, and they don't see the pattern. Yes? 2 questions.
You add 1, and if you added too much, it would make it negative. What happens if you subtract them? What if you rather than 7, you put 5 there?
Then the pluses and minuses reverse. All the questions you're asking can be answered by the algebra, so let's do that, because as the math professor in me wasn't going to let you get away without seeing it anyway. And it will show you other patterns that I didn't reveal, okay? So this is not just me getting my math conscious satisfied, right? I have A, B, C, and D. They can be any 4 numbers. They could be 1-digit numbers. They could be 2-digit numbers. It doesn't matter, okay? So I have, and we know the total is A plus B plus C plus D. Okay, now we know this number has to be what? B, all right? And this number has to be what? C, all right? So this is B, this is C. Those aren't going anywhere. All right, now remember what I said. The only number you don't want to put here is a C. If you do, let me show you what happens. If you put a C here, then in order for this diagonal to add up, this number would have to be A. And then for this group of 4, this would have to be B, right. And then for this group of 4, we have A, C, B, D. And for this group of 4, A, B, D, C. And then if I go down this column, this would be a D. And for the middle, this would be a right, C, D, A, B. And then I have B, D, C, A, and C, B, A, D. Oh, and let's not forget this one, D, C, B, A. So this is what mathematicians call a Latin square. The same numbers appear in each row and each column. Mathematically elegant, magically boring, right? So we adjust things by tweaking this C. So let's call this C plus, which might have been some of the math grades in the audience, I'm not sure. But let's not trigger anything. C plus means that this number here would have to be, in order, here, I'll put these in red. If C plus any number, it could be C plus 1, it could be C plus 2, it could be C plus negative 1.
But what you're suggesting that we do is C plus 1.
Is C plus 1. Think of that as meaning C plus 1, but it really could be C plus anything. It could be C plus X. X could be positive, could be negative, but in what we're going to do, we're just adding 1. So C plus is my shortcut for C plus 1 for saying that. All right, and that would mean that this A would have to be A minus, right, in order for this diagonal to add up. Okay, now we go to this group of 4. This B becomes B plus, right, so that these 4 add up, right? And now this D would have to be a D plus, right, for these 4 to add up. And then for these 4, this C would have to be a C minus, right? 0, 0, plus, minus. Now let's go down that diagonal. I have the A and B aren't going anywhere. This is a C minus, so this has to be a D plus. Notice these two things are equal, right? That's what the algebra says. All right, we go to the middle. Plus, plus, minus, minus, right, for that middle term. All right, now we go, oh, and what about this row? Plus, plus, minus, minus. Again, notice both of those A minuses are equal. And then let's go, this column works. Look at this column, B, D plus, C plus. This A would have to be what? A minus minus, yeah, A minus 2, right? In other words, in order for this group of 4 to work or this column to work. And what about this D? I've got a minus and a minus here. This would have to be a D plus plus. And notice this group of 4 has 3 pluses and 3 minuses, right? And I think that's it. We've now marked up this is the algebra of the magic square. And now you can check that every row and every column and both diagonals have an A, B, C, and D in it. and all of them have an equal number of pluses as minuses. So it's like chemistry, right? So you do the same number of pluses as you have minuses, and that's why everything's going to add up to your A plus B plus C plus D. It also allows, even things you weren't trying for, like we didn't explicitly mention this diagonal, but check it out. We've got A, D plus, B minus, C. It has to add up, right? It's got an A, B, C, D, and a plus and a minus. And again, that plus and minus, we normally mean it means add 1 for plus, but it could be add 2, it could be add 3.5, it could be add -1, right? Notice what I said about negative numbers here. If A was 1, if this was January, then that A minus minus at the bottom becomes -1. All right? So if you're a January and you just follow my rules, you will have a -1 here, but everything else will be 0 or higher. All right? So you might say, and what I do is if I have January, then instead of adding 1 here, I subtract 1 there, and now this A minus minus becomes an A plus 2. But this D double plus can go negative. So if it's January and this ends in 1 or 0, then you just have to deal with the negative sign, right? But 95% of the time, more than that, almost 99% of the time, you can avoid getting a negative number. Yeah? Totally fine. Yeah, this is independent on whether A and B was, the only difference might be if, let me look at this. Yeah, no, I think if we were in another country and, yeah, whether this was like, 19th of March, you'd have 19 here and 4 there. And that's the beauty of algebra. It all still works. Well, that is the one thing that this does. The one drawback to this method is that the numbers can't, if these numbers on top are somewhat out of whack, then the numbers down, if you have one big number, then there will be a big number in every row and column. But I think most people seem to be fine with that. I think the other benefits outweigh that. But yes? No, I never change it more than 1. Here's what I do. So let's do, like we did it with Blake's magic square, and I didn't hear people complaining that because we had a 20 and a 10, right? Let's see, do we have someone else in the 2000s who'd like to have their birthday done? Okay, how about yours? What's your birthday? All right, February 16th, 2007. Okay, so 2/16/2007. So when I'm in the 2000s, I do 20, and then I'll write 07. If it was 2000 even, I'd say 2000. If it's 2001, I do 2001. All right, but in the 1900s, I don't put, like 1999, I would definitely not do 19 and 99. That 99 would be way out of whack. I'll just say if you were born in 99, I'd have a 9 here and a 9 there. If you're 1998, it's a 9 here and an 8 there. But once we get into the 2000s, at least for the next few decades, I'll be putting a 20 here and a small digit, there. I'm not, and I don't even really worry about the negatives. I think negatives can even make it interesting. Like, I can even say in advance, oh, this is interesting. I think we're going to have a negative number in here. And it's like, oh, he saw it all that way, So let's continue this. So, and there are some features of doing it with 20. And since most of the time, and as the years go on, more and more people are born in the 2000s, there's a couple of shortcuts worth knowing. All right, so we start with, okay, you lead the way. This number has to be what? 16. This number will have to be 21. Now let me pause to say, so for everyone born in the 2000s, this number is 21. And I'm going to tell you that this number here is always 19, and it's refreshing not to have to calculate the 19 when you get to this step. So if you have 21 here, there's 19. Yeah, you're looking. If this is C plus 1, this is C minus 1. Those numbers differ by 2. Right? So, but anyway, 21 here, 19 is going to go there. Okay, let's keep on going. Oh, well, yeah, you do have to do that. So we got 8, thank you for that. 18, 38, 45, that's right. I almost missed that. For those who need it, yeah. So, yeah. All right. We'll do the blindfold magic square next time, right? Okay, so now we do 16, 21, and 7. Let's see, 37 plus 7 is 44, which makes this a 1. And then I go to here. All right, I'll do it quickly. So I got 28 to get to 45. That's a 17. This is 37, makes that an 8. You don't have to do this one because you know it's going to be 19, right? So and you don't have to calculate here because you know it's going to be 8. You just slide that number down, right? So this is an 8. Then I go to the middle. 21, 29, 30 makes that a 15. Then I go to here, 37, 45. Hey, makes that a 0. That's your A minus minus at work here. There's your 0, right? If this had been January, this would have been a negative 1. All right, then I go to 21, 15, and 0 is 36. That makes that a 9. You slide this one over for your 1. You bring this one down, and there's your magic square. Thank you very much. And the last thing I want to mention is that this algebra chart shows you all kinds of other groups of 4 that I have not yet displayed, right? I mean, we know, things like, yeah, this group of 4, these add up, right? I got B, C, A double minus, D double plus. This group of 4, notice why this group of 4 doesn't work. Let's just point out why, right? It doesn't have an A and a B in it. Yeah, and this group of 4 doesn't have a C or a D in it, right? So we know those aren't going to work. But everything else is going to work, including ones that I haven't yet mentioned. For example, if you were to draw a 3 by 3 box, and you look at the numbers in the 4 corners of that box, A, C, B minus, D plus, that's going to work. Right? I have seen magicians, by the way, I don't do this, but I think it would look really nice, is they have frames. And they put a frame over it, and you could see, maybe the only 4 numbers that you see are these 4 numbers. Hey, look at these numbers. Then shift that frame over and look at the 4 corners of this, B, D, A minus, C plus. Or take that frame, slide it down. You have C minus, A minus, D double plus B. Slide that over, D plus, B plus, C, A double minus, right? So lots of things you could do there. You could take, here's a little trapezoid. If you take, this is a fun. Yeah, so that's a David Berglis idea. And if you see, there's a wonderful video of his doing something where he had like a whole bunch of different sheets of cardboard filled out with numbers, and then those numbers were brought together in very poetic fashion and to create different combinations. So great fun, for sure. And those frames are a nice way of revealing so the audience isn't so distracted. Like, it would be harder for me to say, hey, take these 4, 2, 20, 15, 8, these 4, 16, 7, 1, 21. I mean, you can only do so many. I mean, the audience is pretty excited with just everything that you've shown them. But there are more things. Like here's a pentagon, B, D plus, A minus, C. See that pentagon? Bum, bum, bum. Did I say pentagon? Trapezoid. I don't know math. Okay, let's do this group of 4. A, C plus, B minus, D. Anyway, I think there are over 3 dozen, maybe as many as 40 different groups of 4 which will add up to A plus B plus C plus D. So the pan-diagonals, yeah, these 4. Anyway, yeah, explore. You have all the math in front of you that you need. Yes, sir. Repeat the question. What age and audience? When I do my shows, I will do like 3rd grade and older. And they love it. I mean, to them, it's math being presented magically. Yeah, no, it's great fun. In fact, it makes for a wonderful elementary school or middle school exercise, right? Because if you first said, hey, create a magic square out of your birthday, it's kind of impossible. But if you give them a little bit of structure and instruction, it's suddenly something they can do.
And the fact that, I'm sorry.
Go ahead, Danny.
And the fact that we're seeing repeating numbers in every birthday magic
in a way, it's forgiven because I have the final, the final button at the end, the 2/16/2007. And I say it as 2/16/2007, reminding the audience that it's a birthday. And I have other methods of doing magic squares where the magic square is nice and smooth. They're practically consecutive. The person on stage can choose the order, but it's not personalized by the birthday. And
Feel for entertainment value, even though this has some,
uh,
let's use the word
aesthetic.
inelegance
Yes.
because of the repetition, it still overcomes
I-
because of the personal value.
I'm going to say that I think this is the sort of thing that a magician might worry about, but an audience member doesn't, as far as I can tell, and judging from the reaction that it gets, and I've done this 1,000 times literally, yeah, they're not complaining. They're saying, "Oh my God, look at all the." They really don't. They really don't. And compared to the other methods, which are a little bit more transparent, like the first method we all learned to do a magic square, you have the numbers 1 through 12 in various parts of the square, and then 4 other numbers, large numbers, to give you the total. That I consider very inelegant and kind of obvious. But this, no, is so far away from that. I've been fooled by other people who did different variations on this, and I didn't see the pattern, you know. So, yeah.
Let me understand it. Aren't all magic square solutions going to have repetitions?
Oh, no, 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 no. And if you want to see me at a break, I'll show you, I'll tell you the other way of doing this without repetition is this is a magic square that adds up to 45. Let's say on a crib sheet or somewhere else, and if you went to my lecture on the first day, we had a magic square that added up to 34. 34 and 45 differ by 11. You could add 2 to everything in that square, and now everything in that square was different. Now if you add 2 to every square, now it adds up to 42 if it was a 34 square. Add 8 to everything, everything's going to add up to 42, and everything is going to be different. And then for 4 of them, I'll add 3 extra, and now everything's different, practically consecutive. It's a beautiful magic square. It just doesn't get the personalization or the punchline.
Unique to the
For the birthday magic square. And it's not the only way to create a birthday magic square, but it's my way, and I'm happy with it.
other magic square solutions, you'll have a different algebra.
There are dozens of different algebras for magic squares. And there are, just to create a single magic square with the numbers 1 through 16, there are 880 completely different magic squares out there that can be done. There's just oodles and oodles of them. Yes, sir?
Could you just illustrate, had that been January rather than
Sure.
44,
If this had been January, again, either just follow the rules and you'll have a -1 over here and live with it, right? Again, in the same way that the audience doesn't seem to mind if there are numbers that are out of whack, they don't seem to, or repetition, they don't seem to mind with the -1. It almost makes it a little more exotic. Like, oops, you dropped the ball before, but look, it still works, But what I would do in that situation is if this had been January, I'll put it as a 1, then if I want to avoid this negative number, all right, and it's going to work as long as this number wasn't 1 or 0. If this number is 1 or 0, well, you're going to have the negative number. But if it's a 7, all right, what I do is instead of this number being 21, I can make this number a 19. Instead of adding 1 to this, I'm subtracting 1 from this. That means that all of these pluses and minuses swap. All right, so everything that used to be a plus is now a minus, the plus represents the number -1. All right, and now A minus minus is now becomes A plus plus. So now it becomes a 3. Instead of 1 minus 2, it becomes 1 plus 2. All right? And that's the reason. Okay, another question, yeah?
Instead of writing down just the single-digit numbers, so like for 8, like that 8 right there, right? Instead of writing down 8, you write down the square root of 64 to break up the monotony.
make it look harder by putting in things like, instead of 8 writing the square root of 64, instead of 9 writing, I don't know, 3 times 3, like some of those clocks that have the numbers 1 through 12 as math problems. I think the audience would really hate me. It's the biggest challenge of my show is to get the audience not to hate me, right? It's just smile throughout, and they seem to be okay with it. And by the way, I'm going to say the reason I think my show works is because before I ever stepped up on stage doing math, I spent at least 4 years of my teenage life doing magic for children. I was the great Benjamini, you know, there might be some former kids in Northeast Ohio that say, oh, you're the great Benjamini, right? You know, and I learned how to talk to an audience, or at least how to get them engaged, have fun. You know, there should be a punchline, there should be an arc to your story, there's audience participation, all those things that we learn as a magician. And that's why I became a teacher. That's as a professor. I have a captive audience. They're not even allowed to leave or heckle me, because then they'll lose points, right? I mean, that's a great position to be in, to have.
When you teach,
Yeah.
when you teach, what's the course?
So I teach at Harvey Mudd College in Claremont, California. The classes, our students here are very smart. They've all had calculus in high school, so we're talking about classes like Calculus 2 and linear algebra and discrete mathematics and probability statistics, combinatorics, number theory, courses on mathematics of games and puzzles. You know, those are the fun things that I enjoy teaching. And
Do you have this same level of enthusiasm when you're teaching?
do I have the same level of enthusiasm? I don't think I'm jumping up and down quite as much in my classroom, but what I learned from being a children's magician is I'm calling on my students. I'm making a point to memorize their names before the first day of classes. I use their pictures, so I'm good at calling out their names, although I do it as a memory experiment, right? I've pre-memorized their names and faces from typically in the 25 or so students. Not 100, but enough that I'll then go through the class and I'll ask them each to give me their name, their nickname, make sure I'm pronouncing it right. And then I say, now it's going to take me a while before I have it 100%, but let's see what we have here. We have Danny here, and we have Joe, and we have. And that also sets a certain amount of, okay, this guy. But anyway, I think honestly, and I just want to say, we are in the best profession. We have the best hobby, and I know very few of us are full-time professional magicians. I think it makes for the best and out there. So I'm a professor and a magician, and that magic helps me in my teaching. And to be honest, my being a member of a large academic community helps me in my magic. Most of my shows, half the shows I do at least, are for other colleges and schools. And that just, even if your goal, and now I'm looking at some of the younger members of the audience who say, wouldn't it be great to be a magician full-time? I think it's great to be a magician and something else. If you have other great talents, use them, combine them. And I think you'll succeed in both venues very well for it. So, we'll take a couple more questions, and then we're going to take our break, and then we'll go on to some other things. But yeah, more questions on that.
So how do you deal with like palindromic type birthdays? Like if somebody had April 4th, 1944.
April, yeah. So luckily, I mean, occasionally I'll get something like 9979. Now it's going to be. It just means that it's not going to all be equal because, again, these A's, B, C, and D all get tweaked, but the numbers will be close together. And I could, if I wanted to have a little more spread between them, I could make that C plus mean C plus 2 or C plus 3. And if I want to sacrifice possibly getting some negative numbers in there, but to have more breathing room among the numbers, that'll work. And you don't have to do, and all that means is, instead of taking this 20 and adding 1 to it, if that was like 9979, you say, all right, I'm going to instead of adding 1 to it, I'll add 3 to it. And now the numbers are a little bit more spread out. Okay, so that's all. No, you don't have to do anything different in your math. And these numbers will still be the same, and those numbers will still be the same. So everything will still work out. Yes, please.
Seems to me that if you get given a date with a lot of like adjacent numbers, like June 5th, 2004, where you have a 6, 5,
5, 4. Well, that's what we had with Blake.
you'll get a lot of
We saw with Blake's Magic Square, who had a 6, 5, and 4 in his birthday, that there were an unusual number of 5s in the square. But judging from your reaction from when you saw it the first time, that didn't seem to negate the experience. It just seemed like it was, oh, wow, still look at all those things. For all you know, there's only one way to do it. And that's what, it has to be that way, right? So, yeah, another question. Oh, very much so. The question is, do I do other magic tricks sometimes to just break the ice? Not that much if it's not related to the math lesson that we're doing. Like when I teach discrete mathematics and we talk about some number theory and properties of, say, the number 9, I will do the missing digit trick in that, the casting out nines trick based on that. And then I'll do that as an opener, and then by the end of the class, we prove why that works. When I teach graph theory, there's a trick that you've seen with dominoes and linking the dominoes together, and that can be explained from the graph theory. They kind of know, and I'm more likely to do a magic trick if they come by office hours and I just say, hey, can I show you something cool? And then it's just, then it just makes you the fun professor. But let me also say, when I do my shows for lay audiences, and you may not believe this, I begin with the invisible deck. Because I want my audience to not be thinking like, this is supposed to be like a fun math talk. That doesn't sit well. And I say, hey, before I get started, I got a quick question. I show a card trick that's never been seen before because no one can see the cards anyway. I have someone up on stage, and it puts them at ease. And oh, this is a magic show. And they're in the mood to have fun with a magic show. And then I do the stuff that you've seen me do up here, and they all have a good time. So I think, what you do to put them at ease is so important. Yeah, by all means. The question is, when I do my show, do I always explain my methods or do I just show off? And it's just a matter of how much time I have. If I'm just doing a 15, 20-minute set, then it's just like at the gala show last night. There was no explanation. I just did it, right? If I'm at the Magic Castle, and I learned so much from performing at the Magic Castle over the last 35 years that, it's, I just do the set. But when I'm when I have an hour, or when I'm at a school or an audience of teachers or engineers or parents of gifted children, whatever, then I love to go into the explanation. I think the secrets are just as interesting as the performances themselves. And, I love sharing the secret. I won't reveal a secret to a proprietary magic trick. I never, I have the stock answers when they ask how I did the card trick at the beginning, or, the pie thing you saw last night. Those are things those are more magic-y than things I'm going to explain. But but yeah, no, so I won't do something like that. I don't do the pie thing for my educational audiences because I want to be honest with them at the end of the show, to explain how everything works. Yeah.
Do you get teachers asking you, how do you teach kids to multiply left to right?
The question is are my methods at odds with what the students are learning in school? If I say left to right and the teachers say right to left, there's no conflict because I'm saying left to right when you're doing it in your head. When you're doing the math on paper, it's fine to do it from right to left. It's easier to keep your columns in order and everything. That's fine. But when you do the math in your head, then I'm a firm believer that you should do it left to right. And I just don't think there's that much taught there on how to do mental math. The best sources for that are my book, Secrets of Mental Math. You can order it on Amazon or anywhere. It has sold 300,000 copies. So it's out there. You can, it's the only book I know that really thoroughly teaches you how to do math in your head. You can get it on Amazon. You can get it on Kindle. Yeah, you can get it on Kindle. I don't know if the graphics are, at one point the graphics were a little wonky on Kindle, but I think they're fine now. That book's been out for a while. I also have video courses. If you get the great courses, Wondrium, I have video courses on, 6 hours on how to do mental math. Everything I know is there, along with other video courses. In fact, here, go stand up, show the book. So there's The Secrets of Mental Math. Hooray, yes. Yeah, it's in his library. Public library, hooray. Yes, sir, question. And then we're going to break in just after this question. Yeah.
Can you talk about the mnemonic devices you're using?
I'm so glad you asked talk about the mnemonic devices, the phonetic code. Stay tuned for part 2. So I'll see you all at 12:30 sharp, all right, and we'll get started on the second half. Okay, thank you. All right, well, welcome back. Gosh, there's probably more that I want to tell you than we're going to have time for here, but I love going in depth. Thank you for all the deep dives that we've been doing. So I think the next thing I want to explain to you, which I have not had a chance to do at all this conference, is to first explain how to do the calendar calculating. That's great fun. And then I've got other directions that I can go. So let's start with that. Okay, so how to figure out the day of the week. Let's begin with something practical, and this is how I explain it to my audiences as well. Let's figure out how to figure out the day of the week for any date this year, right, for 2024. And then we'll go on and figure out how to do it for next year and the year after that, and so on. And then we can move backwards, to years like 2000 or before or after or any century. We'll do that too. But first of all, for every year gets a year code, and the code for 2024 happens to be 2. Okay, so just trust me on that. I'll tell you where that comes from later. But 2024 is a 2 year. Every year we'll get a number from 0 to 6. Right, and 2024 is 2. Next, we need a code for every day of the week, and Monday to Sunday, and the codes for that are 1, 2, 3, 4, 5, 6, and Sunday is 7 or 0. And this is really easy to remember because Monday is one day. Tuesday is literally Tuesday, right? Wednesday, the W is a 3 on your fingers, right? There's the W, 3. Thursday is Fours Day. Friday is 5 Day. Saturday is Sixer Day. Sunday is 7 Day, or Sunday is None Day, whichever you'd like, okay? So those are the days of the week. Next, we need a code for every month, and this is the hard part. And I wish it was 1 through 12, but it's not. The codes for that go 6225035146224, and to make it worse, if it's a leap year, the January and February numbers are 1 smaller. They are 5 and 1. Now you're all stop. I just watched you all stop listening right there. Don't. And I'm going to show you how to memorize this list easily, okay? So I use associations. For every month, there's something that will remind me of that number, all right? So January is winter, and winter has 6 letters. February happens to be month number 2. March 2, the beat of the drum. April has 5 letters, or April Fools has 5 letters. May is a 0. If you have a sandwich, you might want to hold the May-O, because it's healthier. A June, bug. Bug has 3 letters. July is a little bit of a stretch, but if you look up in the sky, you might see a lot of fireworks in the sky, right? Is how July is 5. August begins with 1. August begins with A, which is letter number 1. September is fall, and fall has 4 letters. October, you might think of tricks or treats, which have 6 letters, or tricks rhymes with 6. That's another good way to get that. November, you might have 2 pieces of turkey on Thanksgiving. You might write turkey with a capital 2 to help you remember that. And December is the last month, and last has 4 letters. I could probably quiz you on these right now, just having heard those associations once, and you'd have at least half of them. You know, put about 10 minutes of practice and you'll have this list inside out. Okay, that's the hardest part of what I'm about to show you, okay, is learning the month codes. Okay, then now let's figure out anyone's birthday for this year. So give us your birthday, sir. Okay, so you say, so we want January 1, you said January 1st, how about that? 2024. Okay, we're just going to do this year, then we'll get to other years later. So, January normally has a month code of 6, but this is 2024, happens to be a leap year, right? So January of this leap year would be 5, all right? So you said 5. Plus 1, you said January 1st, 2024. 2024 has a year code of 2. Add those together, you get 8. Now you could count here and go 1, 2, 3, 4, 5, 6, 7, 8, and there's your Monday, right? What I always do is, assuming the number is 8 or bigger, is I subtract a multiple of 7. 7, 14, 21, 28, 35, one of those numbers, and I'll subtract 7 to get 1, and one day is Monday. Okay, so you take this number, subtract a multiple of 7, and that tells you the day of the week. Okay, let's do a few more examples. We'll do about 3 examples, so you'll get really comfortable with this. How about your birthday? March 5th. March 5th. Okay, so March 5th. 2024. So March is what? March to the beat of the drum. Okay, so there's 2. For March 5th, we add 5, just to add this number. Okay, and for 2024, we always add 2. Add those together, we get 9. What are we going to subtract? 7 to give us 2, and Tuesday is Tuesday. Yes, right? So that is this year, your birthday will be on Tuesday. Let's do one more birthday, maybe one with larger numbers in it. How about yours?
October 24th.
Okay, October 24th. All right, well, the odds were pretty high that it would be a matching birthday. Not high that it would come out so soon, or among the first ones. I had a funny thing happen in one of my classes the other day. I was doing one of these experiments, and 2 people in the classroom had the same birthday, and what made it really weird was it was also my birthday. There was like a whole triple of it. Anyway, October 24th, 2024. October 6, tricks, right? 6. For the 24th, we add 24, and for 2024, we add 2, which gives us 32. We subtract from 32 what? 28. 32 minus 28 is 4, and 4's day is Thursday, yeah. And so your birthday this year will be on a Thursday. Okay? Everyone good with that? Everyone understand what to do for this year? I will tell you, this is one of the most practical things that in my magic that actually I use in my daily life. I mean, it's not every day that someone asks you to square a 3-digit number. Maybe me, but not, you know. But it is every day that someone mentions a date to you, and it's real handy to know. You know, I just know this is a 2-year, and you're literally carrying that information with you wherever you go. Okay, so that's good for 2024. What about 2025? Well, what normally happens to your birthday as you go from one year to the next? It goes up a day, right? Why is that? It's because normally there are 365 days between your birthday, And 364 happens to be a multiple of 7. If every year had 364 days, your birthday would be on the same day each year. That would be boring, and that's why they don't do it that way. Right? Really? No, or something about the earth and the sun, right. But with 365, that causes a bump, right? So, the code for 2025 will simply be 3. For 2026, it'll be 4. For 2027, it'll be 5. Now, 2028 is a leap year, right? And so they're going to be most of the time they're going to be 366 days between your birthday. So that means we have to leap over the 6 to get 7, right? So 2028 leap year, you add 2 to get 7, and since 7s and 0s are essentially the same, we're subtracting 7 at the end, we can just bring that down to 0, right? So 2028 will actually be a 0 year. And we'll just go one step further. If it's 2029, that'll have a year code of 1, all right? And so on, okay? Now, this is the reason, by the way, that the month code for January and February is 1 smaller, because we're treating 2028 as if the year has already leaped. Right? When I said there were 366 days between the birthdays, that assumed it was after February 29th, right? So if it was a month of January or February in a leap year, you should subtract 1 somewhere, either from the year or from the month code. I do it from the month code, okay? So that's why we have that. And so why does this work? 2000 gets a year code of 0, a year code of 0. I just set it that way, okay? It's 0 because I want it to be there, and then I adjusted the month codes accordingly, right? I set the days of the week, Monday through Sunday, to go in this order. By the way, I should tell you, giving credit here, I first learned how to do the birthday calculations from a book that many of you own, 13 Steps to Mentalism by Tony Corinda. In book number 3 of the 13 steps was all about doing, lightning calculations and calendar calculations and night's tours, and that was the book that really excited me. And I'd have to be honest, I'm still using the codes in my head that I learned from that book, not the codes that I'm giving you here for these month codes or these year codes, because I'm teaching you a better system, right? In Corinda's book, day number 1 was Sunday, but that to me was awkward. I think of the working week as Monday to Friday, 1, 2, 3, 4, 5. I wanted Tuesday to be Tuesday. There was a different set of numbers for the month codes to learn, and that's actually what I'm still doing on stage, but I'd rather explain it to you the way you should learn it now, where 2000 is 0. Okay, so with that said, 2000 is 0. Why is 2024 2? Well, if you shift the number, we go 24 years, the calendar is going to shift 24 times, but for some times it's going to shift an extra 1, right, for those leap years. How many leap years are there between 2000 and 2024? 6 years. 24 divided by 4 is 6. Right, for 2004, 8, 12, 16, 20, and 24 for those 6 years. So the year code for 2024 should be 24 plus 6, which is 30. Subtract 28, and you get 2. So that's the why the 2024 is 2, okay? Another nice thing to know is that the calendar cycles every 28 years, at least as long as we stay between the years 1901 and 2099, the calendar will cycle every 28 years. So if you found somebody who was born, say, in 1975, you could add 28 to that, and you'd get 2003. And so 2003 is probably easier to work with than 1975. Right? Because 2003 will have a year code of 3, and you're done, right? With the year code there, right? So you can always get in the 2000 to 2028 range by adding a multiple, 28 or 56 or 84, adding some multiple of 28 to get there. I know some people who don't like doing math, but don't mind doing memory, that they just memorize the year codes for 2000 to 2028, and then add to get into that range accordingly. Okay? Question.
Go from 64, how would you?
For 64, you could add 56 to that, or add 28 twice, but let's add 56. So 64 plus 56 is 120. So 1964 will be the same calendar as 2020, right? And what's the year code for let's do this. What's the year code for 2020? You start with 20, last 2 digits of the year, and add what? A quarter of that. That's adjusting for all those leap years. 20 plus a quarter of 4 is 5. That's 25. And 25 minus 21 is 4. So that would be the year code for that.
You know 2000 is year code 0.
Yes.
How do you get the year code for 26?
Let me just do that one more time on a clear sheet. For 2016, I add a quarter of 16, which is 4, to get 20. Subtract 14, that's a multiple of 7, to get 6. That's the year code for 2016. I'm going to do one more example. If it was 2018, okay, I take 18, I take a quarter of 18, which is 4 point something, but ignore the point something, to get 22. All right, so a quarter of 18 is 4 point something. 18 plus 4 is 22, minus 21 is 1, and that's the year code for 2018. It's 1.
21 being a multiple of 7.
21 being a multiple of 7. So this is a multiple of 7, that's a multiple of 7, right? You could use 22 or 20, but why not? Let's simplify it and make the number as small as possible. Because we're going to be subtracting multiples of 7 anyway, we may as well do that now, because once they say, oh, I'm on the 24th of the month, you want to exactly give them the answer. Let me take Blake's question, then we'll move on to something else. Yeah?
Sorry, why exactly are you subtracting the 21?
I could stick with 22, but because I'm going to be subtracting multiples of 7 when I'm doing this anyway, I'd rather subtract that multiple of 7 now than later. You can't subtract the multiple of 7 until you've taken this step. You know, I can't turn 2016 into 2002. That's a no-no. But 2016, after I add a quarter of it, and I get 16 plus 4 is 20, now I subtract my multiple of 7 to get 6. And I'm literally holding on to that 6 when I ask for their month and then their date. Okay? And then
You're adding a quarter of because of the leap year.
because 2016 is 16 years past 2000. And if none of them were leap years, then the code would be 16. But I have 4 leap years, 2004, 8, 12, and 16. And that's the added 4 that's coming there. And for 2018, it's still the same 4 leap years that's coming there. 2012 would be 3. So 12 plus 3 is 15. I'm going to add, subtract 14 to get 1. It's in my book. It's on the video. Yeah, let's, and we got stuff for sale outside the door. No, that's right. So, yeah, we'll leave it at that. Again, if you want to just know the codes from 2000 to 2028, that might be easier for those who prefer to do the memory over the math. I have another book out called The Magic of Math, whose subtitle is Solving for X and Figuring Out Y. Thank you. I'm proud of that one. I wrote the book so I could use that subtitle, honestly. And it's and that's all about the joys of numbers like E and pi and algebra and geometry and the joy of the number 9 and all kinds of fun mathematical things, many of which are motivated by magic tricks, and so that's in there. Yes, sir.
Since
Oh, yeah, so there's a great book on algebra called The Joy of X, which written by Steve Strogatz too. Let's see, other questions. I'm looking at our time, and how about we move into, there was a question at the end about the phonetic codes, the memory stuff. So let me do that, unless, yeah, I think we'll just do that. And so when the problems get very large, I need to resort to mnemonics to remember my numbers, okay? And I first learned this in a book called The Memory Book, co-authored by Harry Lorraine. I read it in high school. But the code that we're going to show is called the Major System. It's been in the English language for over 200 years. And here's how it goes. Every digit gets a consonant sound. So for instance, the 1 is the T or the D sound. The 2 is the M sound. The 3 is the M sound, and so on. Here, let me write the rest of them here. Notice they're all consonants. You're not going to see any vowels on this list. And there are even mnemonics for learning this list. And this is way even easier than the month codes, right? The 1 is a T or D sound, the T or D sound. A typewritten T has 1 downstroke. A typewritten N has 2 downstrokes. The M has 3 downstrokes. 4 ends in the letter R is how I remember that 4 is R. 5 is an L. If you put the 5 on your fingers, you look between your index finger and your thumb, you will see an L. It's cheap, but you'll remember it. That's all that matters. The 6 is one of the sneezing sounds, the ch, sh, or j sound. The backward 6 kind of looks like a J or a nose that's about to sneeze. 7 rhymes with Kevin. It's one of the k or g sounds. 8 is an F or a V. A skater does a figure 8. It's one of those. 9's easy to see. It's a backwards P or an upside down B. And here, you tell me, 0 is S or Z. Why would that be? 0 begins with Z. It's one of those hissing sounds. Once you have this code memorized, you can use this to memorize all kinds of things. You could use it to memorize, you memorize your phone number, you can memorize birthdays, you can remember credit card numbers, digits of pi, right? Here, someone give me their credit card number. No, okay, let's do digits of pi, all right, and this is legit. Here are the first few digits of pi, and then I'll show you how I memorize it, okay? Don't recite it with me, you're messing me up. Come on. Anyway, here are the first 60 digits of pi. Thank you very much. Take my word for it. I think there are some people in the audience who are reciting along with me. But all right, so all right, here they are. So so here's the method I use for memorizing these, and I find this is helpful for me in other phases of life, including mental calculation. Every digit gets a consonant sound, and so with 3, 1, 4, let's see, what do I have? I have 3 is the M sound. I might have to switch markers here. So 3 is the M sound, 1 is the T or D sound, 4 is the R sound, and therefore, what words could we create by putting vowel sounds here? What words could we create? Motor, right. Motor. meter, mutter, mutter. Notice matter, even though it's spelled with two T's, the T sound is only pronounced once. This is a phonetic code. You know, spelling doesn't matter in this method, right? So if I take the next two digits, 1 and 5, 1 is a T, 5 is an L, for me, you just have to see the first 5 digits become my turtle, right? My turtle, and my turtle can only become 31415, right? So if you have the time to study the numbers, you can create silly sentences like, my turtle Pancho will, my love, pick up my new mover Ginger. I'll say it again. My turtle Pancho will, my love, pick up my new mover Ginger. If you say that 5 times, you'll unfortunately have it memorized. And with that, you'd have the first 24 digits of pi. The next 17 digits, which are my movie monkey plays in a favorite bucket. But I like the next 19 the most. They say, ship my puppy Michael to Sullivan's back rubber. And that gives you the first 60 digits of pi. If you want to get to 100 digits, I won't write the next 40 down, but I'll give you their sentences. They are a really open music video, Cheers Geneva Jones, followed by have a baby fish knife so Marvin will marinate the goose chick. Thank you very much. No, I'm going to give credit to, I learned the first 10,000 digits of pi by a method by Vincent Haydan. Okay, I'll leave it at that. But as a mathematician, I mean, I get very excited when I see pi. Pi shows up in all aspects of mathematics, right? The math professor in me wants to remind you that if you take a circle, it's got a radius of 1, then the area of that circle is pi, that you can approximate pi lots of ways. You could write it as, say, 22 over 7. That's approximately pi, but that's not exactly. 22 over 7 is like 3.1428, so it's almost. And years ago, on Pi Day, March 14th, I was invited to write a song to celebrate the number pi, and that's another one of my passions. I love writing parodies, and so I'd like to share it with you. Before I launch into my grand finale here, I want to share with you a song that I wrote to celebrate one of my favorite numbers, if only to convince you that there's no connection between talent in math and talent in music, okay? I'm a living example, and here's how it goes. A long, long time ago, I can still remember how my math class used to make me snore. 'Cause every number we would meet would terminate or just repeat. But maybe there were numbers that did more. But then my teacher said, I dare ya to try to find the circle's area. Despite my every action, I couldn't find a fraction. I can't remember if I cried the more I tried or circumscribed, but something touched me deep inside the day I learned of pi. Oh, pi, pi, mathematical pi. Twice 11 over 7 is a mighty fine try. A good old fraction you may hope to supply, but the decimal expansion won't die. Decimal expansion won't die. Pi, pi, mathematical pi, 3.1415926535889. A good old fraction you may hope to define, but the decimal expansion won't die. Thank you. Other questions besides why am I singing into a magic marker? I don't know. Sometimes you just got to, right? that we say the number pi incorrectly. They would pronounce it p. Pi is pronounced p. And I like to use the word 5, and they would say phi, right? Because the Greek letters are supposed to rhyme. But if we are stuck with pi in our educational system, then what can you do? We'll use phi and other letters like that. There's actually a movement in mathematics that almost everywhere pi shows up in mathematics, it's usually preceded by a 2. 2 pi is actually maybe in some ways more fundamental than pi. And if we could go back in time a few hundred years, we would be celebrating what the number they call tau, which is 6.28 something, because it actually makes the math a little bit simpler. There was a movement for a few decades. I've seen textbooks that say tau compliant and stuff, but I like, so I'm a Taoist myself, but I respect the number pi too. Yes?
Would you care to make any comment about what kind of math should be taught in elementary and secondary?
Oh, what kind of math should we be teaching? You know, what are some of the things I'll say about that? I do wish there was a little more attention in the early grades to mental math. That is, in the real world, you are more likely to be doing math in your head for the simple things. You know, you're reading the newspaper, you're hearing a speech, you're just trying to make sense of what you're about to buy. You know, it's good to have good number sense, and I think learning methods for doing things on paper is not something you do all that often. You do need to learn the rules, the algorithms, but I wish a little bit more attention were paid to mental math. I think in the higher grades, we do everything, after we do arithmetic and algebra, we are pointing everyone in the direction of calculus, and I think if there needs to be a tip of the pyramid, it should not be calculus. Nobody uses calculus in their daily life on an everyday basis. I'm a math professor, I use it in my research, but it's not, I don't, in a normal day, think about how calculus would help me solve the problem. What should be there is probability and statistics, because that is something, and we're starting to see that. I gave a TED Talk on this back in 2009, and I think now that data science and the information revolution that we're in, people are starting to appreciate how important it is that we be able to make sense of the numbers that are just surrounding us. And we take calculated risks every day, whether it's personal risks or things that we're purchasing. And to be able to actually be able to calculate those calculated risks is very helpful, and it's fun. I think more people would have fun learning a relevant subject like probability and statistics, more so than the tools of calculus. So, eventually, those who go on into math and economics and science, engineering, they do need to have their calculus, but I think for the everyday person, we should have more of a background in probability and statistics. So. I'll get off my soapbox for that. Any other questions before I launch into my grand finale? Okay, and I will take questions and meet up with people afterwards. So if some people were asking about some of the merchandise I had after my lecture, I can make those available if you want to see that after the show. But let me conclude with, I think I had the phonetic code over here, so I'll leave that up here. I'm going to try to square a 5-digit number, but to make my job more interesting for you as well as for me, I'm going to do this problem thinking out loud. But my hope is, now that you've learned about how I square numbers, how I memorize numbers, that when I think out loud, it'll make a lot more sense to you. Okay, let's create a random 5-digit number. How about the third row here? If I can get the first 5 of you, call out a single digit. That will be the 5-digit number that I'll use. 8. 2. Which, by the way, were Julius Caesar's last words. Many don't know he was solving a math problem before he got stabbed. 8, 2. Anyway, sorry. I couldn't help myself. All right, next. What was that? 4, okay. Brute, indeed. Did you say 5? Okay. And one more. 9, okay. 82,459 squared. As I'm writing this down, I'm looking at what can I exploit here? I mean, I know how I'm going to square 82. 80 times 84 plus 2 squared. I know how I'm going to do 459, 500 times 418 plus 41 squared. But how am I going to do this? It's helpful if a number is factorable. 82, not so much. It's 41 times 2. 459, well, that's 9 times 51. I like the 50. I'm going to take advantage of that. I'm going to do 51 times 82, multiply it by 9. I'm just giving you sort of the play-by-play. I'm thinking about this as I'm talking to the audience. And anyway, so what I'm going to do is I'm going to take 82 squared plus 459 squared plus 82 times 459 times 2, add them together, and with any luck, arrive at the answer. And one last thing, while I do this calculation, you will hear not just numbers, but occasional words enter the calculation. You now know what I'm doing. I'm using this phonetic code. I don't want you to think you're seeing something crazy happening up here. One last instruction for my judges with calculators. Who's got an answer? Raise your hand. Good, a bunch of you. Should have a 10-digit number beginning with 6, ending with 1. In between, I don't know yet. There's a 50% chance that I'll make a mistake somewhere in the middle. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that I got the answer right, because this is my big finish. So, without any more stalling, and I have been a little, here we go. I'll start the problem in the middle with 82 times 459. I'll do 51 times 9 and take advantage of that. So 82 times 51 is 4,182. 4,182 times 9 is 36,900 plus 738 is 37,638. 37,638, double that to get 75,276. 75,276 becomes call, no cash. Call, no cash is 75,276. I think that works. I think so. Okay, that's multiple 9. I like that. Okay, so call, no cash. Okay, next I do 82 squared, which is 6724, so I can say 6 billion. Take the 724, add that to call. 724, oh, this is going to be very close. 724, add that to call. 724 plus 75 is 797 million. No cash, no cash. Okay, finally we do 459 squared. That's 500 times 418 plus 41 squared is 209,000 plus 1,681 is 210,681. Shifty if I needed shifty. Take the 210, add that to no cash to get 486,681. Oh, close. Ooh, shoot. All right. Let's see where we are. This is where the fun begins. All right, so let's see. If I had call, no cash. Call, no cash. First of all, that is a multiple of 9, so I trust the answer. Is it off by just a digit or so? Okay, 1 digit. Okay, so I do 459 squared. That's 210,681. If I take the... It's off by a digit, but it's 2 actual digits. Thank you for that. 210. 210 added to the... So I may have made a mistake on my initial multiplication. Let me try that again. I got 4182 times 9, 36,900 plus 738. 36,000... I'm going to try one more time. 4182, 36,900 plus 738 is 37,638, 75,276. Darn it, I'm still getting call, no cash. Let's see. The 6 billion's got to be right? Okay, and the 681 should be right? Okay, and so if I take 724, add that 724. 724, add that to call. Now I'm getting 799,000. Good. Thank you very much. I hope you enjoyed Mathemagics. I'm Art Benjamin. Thank you. Yeah, what's 2 million? I got to tell you, Years ago, so to answer your question, I did not make the mistake there deliberately. I did not. I make it naturally enough that I don't have to plant them. But I have memories way back when, one of my earliest magic conventions. I performed at Tannen's Jubilee a couple times, once in college and once beyond that. And they had me do like, they had me in part of, it might have been the close-up show. The performers rotate in different rooms, right? And so I did my show 4 times, 2 different rooms, and in two of the rooms, I got the answer, right away, and in 2 of the rooms, I missed it very much like this, and then came back and got it. The reaction was definitely stronger in the 2 audiences where I missed it than the ones where I got it. And I was like, that was a real eye-opener to me. And I was talking to, now help me remember the name, he was a mentalist, he used a crystal ball. Tim Conover. Tim Conover said to me, you have to make the mistake. You have to make the mistake. That is for dramatic purposes, just like when you go to the circus and you see the juggler before they do their biggest one, the tightrope. There's always, oh my God, this is really hard. Look at me. So, but I just let you know that was not a planted mistake, just because you guys deserve the truth. And if you have any other questions, I'm going to happily hang out here. Thank you again very much. Appreciate it. Thank you, Danny. Thank you.